We good to go?
Okay.
If you want to stand on the other side too for the presentation, I can get you.
Oh, okay. Over this side. Gotcha.
Okay, so should we get started? I think let's get started on this. Hello, everyone. It's my pleasure and honor to introduce Professor Heath Hofmann from University of Michigan. And let me quickly read his bio. So Dr. Hofmann received his PhD in electrical engineering and computer science from the University of California at Berkeley in 1998. He was then a faculty member of the Department of Electrical Engineering at Penn State University from 1999 to 2010. In 2010, he moved to the EECS department of the University of Michigan, where he is a full professor now. His research area is in power electronics, specializing in the design, analysis, and control of electromechanical systems. Specific research interests include propulsion drives for electric and hybrid electric vehicles, multiphysics modeling of electric machines, energy storage systems, and energy harvesting. He's currently an associate editor for IEEE Transactions on Energy Conversion and IEEE Transactions on Power Electronics. So without further ado, it's all Professor Hofmann's yours. I'll keep this, probably you have a...
Oh, that's right, I do. Thank you. Well, thank you, Arjit, for inviting me. I appreciate it. You guys can see the slides? Yep. Okay, good. So my talk today is on simultaneous identification and control of electric powertrains. This work has been funded by the Office of Naval Research. I collaborate very closely with Professor Jing Soon, who's the chair of Naval Architecture and Marine Engineering at Michigan. And then we've had a number of grad students, Dave Reed, Jun Hu, Fanny Pinto Delgado, who have worked on this project, and one postdoc, Ziyu Song. So I'll introduce the Michigan Power and Energy Laboratory. I'm learning a lot about Illinois today. I thought I'd tell you a little bit about what we have at Michigan. And then I will introduce the idea of simultaneous identification and control, specifically over actuated systems, of which the examples exist in the area of electric powertrains. And then we'll have two case studies of this concept. The one is looking at hybrid energy storage systems, and I'll explain what those are. And also torque control of permanent magnet machines. So these are the faculty in the Michigan Power and Energy Laboratory. A few of you know Ian Hiskins. This is me. We have some younger faculty, Johanna Matthew and Al Thaddeus-Silvestrus. Johanna works in the power systems area. Al works in power electronics, does a lot of work in wireless power transfer and whatnot. My research is in electromechanical systems, as Arjit mentioned. A few different specific topics that I have here. So traction drives, we're going to get into hybrid energy storage systems as well. I also do some work in the area of magnet-free machine designs, energy harvesting. I've done quite a bit of that work in the past. And then I do a lot of work in developing models of electric machines, focusing on computationally efficient models. So in terms of our facilities, one of the main features of our research lab is what we call the Advanced Electric Powertrain Testbed. At least that's what we're calling it now. I'll probably call it something else in a year or so. But basic idea, the schematic is shown here. We bring in three-phase power, AC power, rectify it to create a sort of load bus, then have a DC-DC converter to create our test bus. This would correspond to the bus voltage of an electric vehicle. We have a propulsion drive here with the DC to AC inverter. Then we have a number of different types of energy storage, a lithium-ion battery pack, ultracap or supercapacitor bank, and a flywheel, all of which interface with the DC bus through converters. The propulsion drive connects with a load machine, which is actually identical, has its own inverter. We have a resistive load bank. that we can use to dump power if necessary. And we have one control system that controls the entire power electronic.
What's going on there with those two machines?
Well, this one represents this is the machine under test, and this represents the load. So you could have it.
Still a motor generator set.
Yeah, essentially. They're identical, so they have the same torque and speed ratings. Here's a picture of the test bed. On the top, we have the resistive load bank, these big green resistors. I have some pictures of the individual parts, which I'll show in a bit. But here on this side, we show the induction machines connected at the shaft. On this side, we have permanent magnet machines, the power electronics, and you can see a little bit of the battery pack here, the ultracapacitors. The flywheel is here on the side. We use inverters from a company called Applied Power Systems. The nice thing about these is that there's no built-in controller. We can provide our own pulse width modulated waveforms to drive the transistors. Permanent magnet machines are 145 kilowatt machines from UQM. And the induction machines are 47 kilowatts from Azure Dynamics, which I don't believe exists anymore. Energy storage, we have these transportation ultracapacitor modules made by Maxwell. These we have 4 of them. We can store a total of 2 megajoules, provide 240 kilowatts of power. We built our own lithium-ion battery pack. These are lithium iron phosphate cells. We have a total bus of, it says 150, more like 144 volts, capable of putting out 47 kilowatts of power. And then we have a flywheel system from Vicon Energy. It's an all-steel flywheel with a permanent magnet motor generator, but it's supported by magnetic bearings. It's spinning in a vacuum, there's a little vacuum pump down here. That could provide 300 kilowatts. So it's not the best fit for our system. The power levels are probably a little too high, but when flywheels, you kind of just have to take what's available. Not a lot of options there in the market. Like I said, we control all the hardware with one controller. Currently, this is made by this company, Speedgoat, which is basically a PC, single core Intel processor. It's got I/O boards with the A to D, CAN board. It's got FPGA, which is what we use for the generating the PWM waveforms. And MathWorks describes this as a turnkey system for their XPC Target or real-time Simulink. They changed their name for that every couple of years as well. And but the nice thing about it is we can develop control algorithms in Simulink. Oh, by the way, my students really dislike this control system. Just so you know, they hate it. They bothered me for a while, so we got a new one. Compliments of ONR through a Durup grant. This is a DSpace Galexio system. It has 3 different processor units, these 2 here, and then there's a board here in this that has a 4-core processor board in it, or quad-core processor board, should say. So we have a total of 20 cores that we can use for control and perhaps real-time simulation as well. This likewise has an FPGA with multiple A to D digital I/O output capabilities. It also allows development of control algorithms using Simulink. We are currently in the process of integrating that into the testbed. A little bit about our instructional lab. We have 8 stations. This is a picture of one of them. Here's the equipment we have. We have a 500-watt supply, electronic load. We have oscilloscopes with power measurement and analysis software. We have a 3-phase 500-watt AC supply, 42 volts RMS, so it's safe for students to work with. We have a motor generator dyne. This is the system that Ned Mohan has developed at Minnesota. We use their system. And we have a DSpace, once again, microcontroller card to do the controls development. So here's a picture of the little motor generator set. Once again, this is made by Motor Solver. This is part of Ned Mohan's instructional kit. So we have permanent magnet machines, both DC and AC, induction machine. And then the power electronics is here. It has 2 3-phase inverters on it, which we can use to control both of the machines here. The power flows around in a loop, which is nice. And we use this setup for some of the experiments I'll show you, as well as the larger test bed. All right, so simultaneous identification and control. So what we're trying to do here is achieve 2 goals simultaneously. We're trying to control this plant. The plant is characterized by parameters theta, parameter vector theta. It has an input, U. I'm not showing a disturbance. Technically, I probably should, but the disturbance is not that critical for the points I'm going to make. And then we consider 2 different types of outputs. We have a measured output Y, and we have a regulated output W. So it's important to distinguish between them. In the case of control, the idea is you're trying to come up with an input so that the regulated output tracks some reference value, W ref here. So this is often what you're trying to do with a plant, is control it. But you may also want to identify the plant. You may want to determine what the parameters theta of that plant are. And in that case, you get into system identification, you get into adaptive control theory. The goal there is to provide an input to the system so that the plant is persistently excited. And there's a long discussion about what that means. But a sort of a simple way of saying it is that the input has sufficient frequency content that it excites all the modes of the system. And in order for us to obtain knowledge of the plant parameters. Now, because persistent excitation requires a lot of frequency content, this goal and the control goal are often in conflict, because the input that achieves your control objectives may not have that frequency content in it. If you're trying to regulate something to a constant value, right, in steady state, your input may be constant, so it's only DC in nature. So this is an issue, and historically, the approaches have been made to try and mitigate the conflict as much as possible, but not eliminate it. Now, in the while we're talking about identification, I'm going to introduce something called the Fisher Information Matrix, you may or may not be aware of. So it's actually, sort of based on random processes. So the matrix is actually the expectation of the partial of the logarithm of a probability density function for an output given a certain parameter. Okay, and so this is a vector. This is a vector transposed. You multiply them together, and you get the matrix quantities. We're going to be showing sort of other versions of this matrix, but this is how it's sort of typically initially presented. Basic idea is where it tells us how much information about the parameter vector is contained in the output. And it does it from a stochastic sense. And even though the plant itself is deterministic, in this case, because our measurements are often infected with noise, you have to look into treat it as a random process and analyze it accordingly. Though, as we'll see, we're able to come up with some other representations of this matrix which are purely deterministic in nature. All right, so we are focusing on a special case of overactuated plants. And in the case of an overactuated plant, the number of inputs, in this case M, is strictly greater than the number of regulated outputs, P. And provided that's the case, and provided you satisfy some other criteria in terms of controllability, observability of the plant, it turns out that you have some extra degrees of freedom that allow you to achieve both objectives, to achieve a desired, regulate the output to the desired value, and at the same time inject the additional frequency content so that you can probe the system and determine the system parameters. So we have two different examples that we're going to talk about. One, you're probably all familiar with, electric machines. So the inputs in this case are the voltages. Three-phase machine, though technically usually only 2 degrees of freedom, because of the zero sequence component usually doesn't do anything for you, so you throw that away. The outputs are the phase currents, once again, in the equivalent two-phase form. But usually what you're trying to regulate is the torque, or maybe you're trying to regulate speed or position, but usually these things all boil down to initially having a torque regulator, and maybe you have an outer speed or position loop on that. But at any rate, the idea is you have more inputs to the system than you have regulated outputs. Yeah. Another one, which is maybe not as familiar, oops, I thought this was animated, turns out it's not. A hybrid energy storage system where we have a battery, in this case, and a supercapacitor bank. For example, in an electric powertrain, you have your inverter and your motor here, but the power to that drive comes from both power sources. You have two converters. In this case, the inputs, you could define the inputs in various ways, but sort of the basic way of describing them are the duty cycles of the power electronic circuits. You have multiple converters, multiple duty cycles. Your measured outputs in this case would be the bus voltage as well as the currents flowing in the battery and supercapacitor. Your regulated output in this case is just the DC bus. So once again, you have a degree of freedom here, which is kind of obvious, right? Because so the drive is requiring a certain amount of power to run. You have two different energy sources. So there's in some sense an infinite number of possible combinations of power that you can choose to still get the same net power on the output, right? So then you can play around with that. All right, so hybrid energy storage, we've focused a lot on battery electric buses. There's a number of potential advantages of adding in a hybrid energy storage system for something like a bus in particular. The basic idea of the hybrid energy storage system is, and this might be a little hard for you to see, right? But we're showing the properties of different types of energy storage, lead-acid batteries, ultracapacitors, nickel metal hydride, lithium-ion, lithium polymer. One thing you can see is that the ultracapacitors actually do quite well in terms of power density, operating temperature, cyclability. Lithium-ion is typically much better in terms of energy density, not so great in terms of cyclability. And so what you can do with the hybrid energy storage system, with a proper energy management system, is you can come up with ways that utilize the best properties of these different types of energy storage. And in particular, one thing that's very desirable is to extend the battery life, right? Because batteries really do not like to see large pulses of current that you would see during a large acceleration or deceleration. Ultracapacitors are much better at absorbing that type of behavior. And so by using the ultracapacitors to deal with those types of spikes, you can extend the battery life and as a result reduce the overall operating costs of the vehicle. So a student, my current postdoc at the time, he was a visiting scholar, did some dynamic programming analysis of a bus where he had hybrid energy storage, and the programming actually had sort of two separate goals. One was to come up with the optimal size of the supercapacitor bank that you would add. And so this is sort of the Pareto front of that optimization. So there's this y-axis is the cost in terms of operating costs per kilometer of driving. The x-axis here is the cost of the supercapacitors. So you see this kind of standard curve here. So probably a good place to choose would be here at the knee of the curve, where you've already achieved most of the reduction in cost, per kilometer, but the actual supercapacitor bank cost hasn't gotten overly expensive. Another aspect of this is the dynamic programming was to come up with the optimal energy management system that achieved the best behavior. And so this was a plot of the dynamic programming results. This is the power drawn from the supercapacitor on the y-axis versus the overall power demand. And from that optimization analysis, it was found that this curve was achieved, provided the bank was large enough. If the supercapacitor bank was too small, things got a little noisier. But provided it was the right size, we saw this interesting behavior where it's fairly linear here, and charge and discharge, and then there's this sort of hysteresis range where you don't draw any power at all. And so that led to sort of, we could actually implement a fairly simplistic energy management system, which effectively just tries to emulate this curve, and that's shown here. But once again, by doing this, we can extend the life of the battery, as well as potentially improve efficiency, and that's where the benefits are in terms of the operating costs. Okay, so hybrid energy storage system goals. We want to optimize power system supply quality, minimize losses, minimize battery degradation. We also want to identify the system for reasons which I'll get into, how we can use that information. And so one of the goals here was to design the optimal inputs to the battery and the supercapacitor to determine the parameters. And so for both the battery and the supercapacitor, we used what's called this equivalent circuit model. There are different models of batteries that get more into the actual chemistries, but we're going with these electrical models in our work. And the supercapacitor is quite easily modeled in this form. And so the goal is to try to determine all these parameters of both models in real time. So the way that we investigate the optimal signals to identify, we use what are called Kramer-Rao bounds. And this is related to the Fisher information matrix. Once again, this is a slightly different way of representing it. But first, we look at the sensitivity of the voltage measurement to the different parameters in the system. If we're assuming Gaussian noise, then we can actually represent the Fisher information matrix as follows, where this is the covariance of that noise, inverse covariance of that noise. The covariance matrix can then be represented as the covariance of the parameters can then be represented as the inverse of the Fisher information matrix, and then what's called the Kramer-Rao lower bound are the diagonal terms of that matrix. And the goal is to minimize these lower bounds in order to essentially maximize the amount of information contained about the parameters. So in this case, we're looking at the battery model. We have a model of the electrical dynamics. We can look at the sensitivity of those dynamics to the different parameters, which are the resistance R sub S and then this RC combination. Convert those into the time domain and then look at a time averaged Fisher information matrix. And in this case, we're looking at injecting 2 sinusoidal currents to achieve the information. Usually with adaptive control theory, the idea is that every frequency you inject allows you to identify 2 more parameters. It's a rough way of describing it, but it's pretty accurate. And so since we're looking at 4 parameters, we need 2 sinusoids. So these are the resulting Kramer-Rao bounds as we sweep in frequency. And so we see that, for example, for R sub S, we actually want to minimize it. We want to operate as high a frequency as possible, which is intuitively true. At high frequencies, this capacitor looks like a short circuit. So basically, this falls out of the problem, and you can extract the R sub S in a fairly straightforward manner. For the other terms, RT and tau, there's actually an optimal frequency, which is related to the time constant. And so you can determine what are the best frequencies. There's some other sort of perhaps obvious factors here, making the signals larger or decreasing the noise helps as well. So we can do the same thing for the supercapacitors. It's a little more straightforward. In this case, for the capacitor, you actually want a low frequency. For the resistance, it actually doesn't matter. It's independent. So these were the optimal waveforms for the battery and for the ultracapacitor. Here's a picture of these again. I already showed them once, but just to kind of give you a feeling, maybe cause you to recollect. So here we're doing our parameter estimation for both the supercapacitor, capacitance, and resistance, and then compare what we predict from those parameters, our estimated voltage with the actual measured voltage. Likewise with the battery, conducting the estimation of the 4 parameters there. Once again, we see good tracking of our estimated voltage with the actual value. And a low relative error. In both cases, less than 0.5%. So what do you do with these parameters? We're looking at a number of different things. So the first topic we looked at was trying to determine the power capabilities of the battery and the supercapacitor, right? And this is important. If you're using this in an electric drive, you want to know how much power your energy storage can provide to the motor so that you can act accordingly, right? And then the parameters, resistances, the open circuit voltage, which represents state of charge, these things will obviously change over time. And so knowing what they are in real time can tell you what those limits are. And so we derive some expressions for both charge and discharge powers for the battery, which depends on the duration of the power, as well as the charge-discharge power of the supercapacitor as well. And then this shows the experimental results for the battery, both for the charge and discharge cases, for the power that could be provided for 1 second or for 30 seconds. Same for the supercapacitor shown here. You see that obviously for 1 second you can provide much more power than you could for 30 seconds in both cases. So this has been accepted in IEEE transactions on power electronics, currently available online, hopefully in press soon. All right, next is AC machines. I don't know how much everyone knows about AC machines, so I feel like I'm sure Erj is doing a great job teaching you about drives. But let's go over it briefly. Here are the main components. You have the electric machine, you have a power electronic circuit, in this case a 3-phase inverter, though there are other options, and a control system. Particularly for electric powertrains, you want to operate over a range of speed. You need a drive to achieve high performance control. The 3-phase inverter provides the power to the machine, right, from a DC bus to generate pulse width modulated AC voltages in the average value sense. These are limited, but the individual phases, the output's limited between 0 and the DC bus. And so this means that your output voltage or your input voltage to your machine is constrained, right? There's only so much voltage that you can apply. And if you're not careful, if you try to exceed that range, you can deteriorate the performance of your system. The current outputs are likewise limited, right? At some point, the transistors will just melt, but probably before that, there's some kind of safety circuitry that will kick in and shut off the inverter and trigger a fault condition. But at any rate, you have some hard limit to how much current these inverters can provide. So we're going to revisit that a little bit later, but I just wanted to point it out now. So control, high performance control of AC machines, sometimes referred to as vector control or field oriented control. Has some basic components to it. One is the Clark transform. It's named after Edith Clark. She was actually the first female professor in electrical engineering at the University of Texas, actually. She was the first one anywhere, but that's where she was. The first author on this paper that introduced the Clark transform, Dusterhoff, he became a professor. I think he's probably a grad student at this point. He became a professor at UT. And I was an undergrad at UT, and I took classes with Professor Dusterhoff, so I can claim some maybe questionable lineage on all this. But at any rate, that transforms the three-phase values into equivalent two-phase values. And then we have the Park transform, which converts from a stationary frame to a synchronous frame made by R.H. Park. I have no connection with him whatsoever, unfortunately. But anyway, you convert into a synchronous frame, and then your control algorithm is implemented in that synchronous frame. For synchronous machines, that corresponds to typically the rotor reference frame. It's based on the electrical rotor position. So high performance drives, which you need for things like electric vehicles, hybrid electric vehicles, require things like high bandwidth for fast transient response and tight regulation, high accuracy regulation of torques or speed or position. One example for HEVs is you have these power split architectures where you have motors and generators and an engine all combined together, and you've got to make everything match up just perfectly in order for it to operate properly, which means you need to be, the machine needs to be producing the torque that you want it to get all that to happen. So this is kind of a control systems perspective on how we do torque regulation. We typically don't regulate torque directly. That would require a torque sensor, which exists but are expensive, a little noisy, not necessarily great in bandwidth. And so they're not the best thing to use for feedback control, or in a product for that matter. And so what we typically do is we indirectly regulate torque through current regulation. Current is something we can't easily measure. And so we often have like a reference torque, which from the machine model, we calculate reference currents, generate an error signal, run those through a regulator, through the plant to get the currents we want. And then there's another mapping from the currents back to the torque, once again, depending on the parameters. Specifically, it depends on the magnetic parameters. The parameters, however, can vary with operating conditions. Stator resistance can vary with temperature and skin effect, which is a frequency-based effect, which means the resistance will change with frequency or speed, sometimes quite substantially, as much as 100%, maybe more. Inductances can also vary significantly due to saturation. This is not necessarily the best way to capture that behavior, but it is one. Permanent magnets, flux linkage can also vary with temperature. Typically, they gets lower with increasing temperature, and it can also drop due to degradation. You can, partially demagnetize the magnets. That results in a lower overall flux linkage. So, because these things can vary over time, being able to determine them in real time through online estimation is highly desirable. Okay, this one was, and so one of the key challenges here is on the torque, getting the actual torque based on the currents that we have. Once again, that's going to be sensitive to parameter error. So here is a model of an interior permanent magnet machine or a buried magnet machine. We have magnets and an iron rotor. Here are the electrical dynamics for those, once again, in the rotor reference frame, the synchronous frame in this case. And then the torque has two components. It has one based on a reluctance torque associated with the saliency of the rotor structure, and a permanent magnet torque as well. And once again, this is the relationship between the torque and the currents, and it's a function of the magnetic parameters of the machine. So first off, we'll talk about a controller that actually utilizes our estimated parameters. And so what we have here is Once again, we do everything in the synchronous frame, which in this case is the rotor frame. And we're assuming we know parameters here. So that allows us to have a feed-forward component to the controller, which is basically just trying to compensate for all the dynamic terms and is based on the parameters. There's a decoupling term here because when we transform into the rotor frame, we get cross-coupling terms. Those cross-coupling terms, if we're not careful, can result in resonant responses, and so that can deteriorate performance. If we, in our controller, we try to compensate for those, decouple them, then we can avoid those issues. We also have feedback, in this case, just proportional feedback. We're actually using the adaptive parameter estimation to act as sort of an integral term to compensate for errors. I guess another point I could make is we have a filter here in order to make some of our transfer functions strictly proper, which is necessary. So we have a controller which is based on, we can use some Lyapunov theory and come up with some current error dynamics. And we can then, using the Lyapunov approach, devise a parameter estimation technique shown here. Gamma is just some gain matrix. Phi is what we call a regressor matrix, and it's based on both measured and command currents, as well as the measured electrical speed. And we can prove that if we use this particular parameter estimation technique, that the current error goes to 0. And this is the controller error. So getting back to the idea of simultaneous identification and control, once again, we want to inject these signals into our system so that we can identify parameters. But in this case, we want to achieve a certain torque. But it turns out that because we have multiple currents, there's an infinite number of possible combinations of current that can generate the same torque. We can describe that as a manifold. And so this is sort of showing some results of the parameter estimation. This is simulation results. But we can see that after the parameters converge, we finally get to the manifold here. And these are the direct and quadrature currents, and this is for a given torque. This is using the instructional motors. It's very small torque, 0.2 Newton meters. And then once we get here, though, we can then stay here, so we can inject the signal. And once the parameters converge, we stay on the manifold, which means we're keeping the same torque, even though we're moving the currents around. And then when we do another step to another torque, another manifold, now that we have the parameters, we can easily stay on that manifold. We're injecting these frequencies into the machine while keeping the torque constant. So once again, we started off using these little motors in the instructional lab. We determined parameters, the flux linkage from an open circuit test. We did LCR measurements on the resistance and the inductance of the machine. So this shows a result. We start off with some detuned parameters. And then we have a couple different ways of estimating the torque. And we show here that at first we have the detuned parameters. Then we turn on the adaptation. The parameters eventually converge to constant values. You see a few things here. You see the resistance. This is a normalized plot, so everything theoretically would go to 1. The resistance is a little higher than 1. This is probably because we're not taking into account the voltage drops across the transistors themselves in this analysis, and so this resistance probably also includes the RDS on the MOSFETs. We likewise are seeing a little bit higher inductance. Because it's a surface mount machine, LD and LQ are essentially the same. This is probably because our LCR meter was not accurately measuring inductance due to going through the rotor because of a solid rotor structure. There's probably inducing some eddy currents, which give us a lower inductance measurement than we would have expected otherwise. The permanent magnet flux linkage pretty much stayed dead on. So we can see that after we turn on the estimation, our torque initially was off quite a bit, but then after the adaptation turned on, it zeroed in on the proper torque. This shows sort of the response of the controller to different speeds. Once again, at higher speeds, you have these cross-coupling terms, which can affect performance. But by getting the inductances, we can decouple those fairly accurately and get essentially uniform behavior no matter what speed we're operating at. So briefly, this hasn't been published yet, but we have been doing the tests on our 145 kilowatt machine. We can see the same thing. We turn on the parameter estimation. We start off with a torque error. Eventually, we zero in on the proper torque. Here are the current waveforms. Once again, we're injecting these signals into the machine to get the persistent excitation without it significantly affecting the torque. And once again, the parameters are pretty much zeroing in on the offline measured values, which once again aren't necessarily true values in and of themselves. All right, so this next part is getting into some model predictive control type techniques, right? So simultaneous identification and control, you could argue is very desirable if you're trying to implement model predictive control, right? Model predictive control requires an accurate model. And if your parameters are changing all the time, then that's going to affect the results if you're not accounting for that in your controller itself. Okay, so we're implementing something like that, but we're doing also something else in addition to estimating the parameters and using those in a predictive controller. We're also using the controller to try to determine what the best excitation is in real time. Okay, so that we get the parameters as accurately as possible. So the other thing that we're going to try to do here, I mentioned how you have voltage and current constraints due to the inverter and to the machine as well to some degree. This allows you, the model predictive control type techniques allow you to actually try to stay within those constraints as well. So how many of you are familiar with the space vector hexagon? Raise your hand. Okay. So if you don't know about it, you can ask someone. But basically, we talked about the Clark transform and how you take the three-phase voltages of the inverter and transform them into equivalent two-phase voltages. This hexagon represents the range of two-phase voltages that the inverter can put out in an average value sense. So, okay, so that's something. So space vector modulation, you can look it up. That's fairly well known. Nothing really new there. Something that isn't quite as much talked about, though, if you actually limit your peak three-phase currents to a certain value, and you do the transforms, you actually get another current hexagon, which is rotated 90 degrees. And this represents the space of currents, two-phase currents that you can command, assuming 0-0 sequence current, which is what you should do. But that you're constrained to fall within this hexagon if you're trying to satisfy that constraint. Fisher information matrix, we have an alternative way of representing that here, which is a deterministic expression, and it's based on the partial derivative of the output with respect to the parameters times the transpose of that. Summation over an interval of time, discrete time. Now, if your plant has a linear parameterization, the output is proportional to the parameters. Hence, you can represent it through this regressor matrix, which we brought up earlier. Then, the Fisher information matrix can be represented in terms of this regressor matrix, a summation, phi transpose. Now, and this actually comes up in some adaptive control theory proofs. If you want to prove parameter convergence, usually you require this matrix to be a full rank. Okay. Now, of course, there's full rank, and there's close to being singular, very different things. And so what we do is we look at the determinant of the Fisher information matrix. More specifically, we look at the logarithm of the determinant because that function has a concavity property. And then there's a paper here if you're really interested in that sort of thing that gets into that in more detail. But basically, once again, if the matrix is singular, the determinant is 0. And so we're trying to maximize our information by making that determinant as large as possible. So we're trying to maximize that as part of our cost function. So we have our overall optimal control algorithm here. It's predictive. We have 2 terms in our cost function that are basically competing. One is we want to minimize losses. And in this case, we're looking at a synchronous machine. I'm sorry, a surface mount machine, a non-salient machine. So LD equals LQ. And so in that case, all the torque occurs with quadrature current. And so we're using the direct current in this case to generate the excitations, and hence try to maximize this term. But that generates loss, and we don't want too much loss, so we incorporate a loss term to try to keep it manageable, right? Then we have a number of constraints. The constraints associated with the fundamental dynamics presented in a discrete form. The Fisher information matrix is not a constraint, actually, just part of the cost function. And then we have the voltage and current constraints that I described earlier. The quadrature current is constrained based on the torque we would like to provide. And then we do a very simple prediction of rotor position just based on the speed and extrapolation because of the inertia of the system. We don't expect the speed to change too quickly within our time horizon, and so that's a reasonable thing to do here. So let's look at a few different simulations. These are all simulation data because this controller takes an awful long time to run. We don't have it running in real time. But basically, we start off where we're trying to do a torque command. We're running our parameter estimation, but we're not injecting any additional signals. And so we see, as a result, the parameters don't converge to their proper values here because it's not properly excited. And as a result, our torque is off because our flux linkage is off. Here is the current hexagon I showed earlier. And we have an initial transient where we're kind of escaping it a little bit. Here, we are injecting a signal that is causing the persistent excitation. And so we're getting convergence. The problem is at this operating point, we're violating the current constraints. We're going outside the hexagon. Here, we're actually employing the constraints. And so we get the parameter convergence, we get the torque where we want it to be, and we're staying after an initial transient where the parameters are off, right? Once the parameters get in line, we stay within the hexagon. So we're exciting the system, we're getting the most out of it, and we are not violating the constraints. Now, this was just based on a low speed condition where when you're operating at low speeds, you're not constrained by voltage because your back EMF isn't large enough to hit the voltage limits. So this is low speed operation. Once you get to a high speed operation, typically you're voltage constrained. And so in this case, we're taking that into account. Once again, we're injecting a signal, doing so in a way that stays within the space vector hexagon, the voltage hexagon. That's more common. And then in this case, we have a medium speed range. This is where you're hitting both the current and voltage limits of the inverter. And once again, you can see we're staying within the hexagon. We're staying within the current hexagon. We're not able to exploit the current hexagon as much anymore. This is the fundamental limitation. But the idea being that once we have these accurate parameters, we can really run at the limits of the inverter capabilities without violating them. So that is my talk. I'd like to thank Office of Naval Research for supporting it and also point out that what we say isn't necessarily what they say. So happy to answer any questions. Yeah.
Just to clarify, the simultaneous parameter estimation, you're doing that at every sampling period, right? So my question then is, thoughts on what loss of performance would have if we kind of backed off and did anything?
Well, right. So, and that one thing that, came up when we talk about the supercapacitor, right? I said how, making the signal larger helps, for a given amount of noise, right? And so if you're concerned about losses, which you are, then you may want to do a situation where you run this every so often with a fairly high level of excitation so that you get your parameters converged, and then you shut down, and then you wait a while, and then do it again. It all depends on how fast you think your parameters are going to change. In a lot of cases, right, if it's due to degradation, then the change is probably very gradual. If it's due to temperature, due to thermal time constants, it's probably pretty gradual. If you're trying to capture the saturation effect, that's going to happen very quickly, so you can't really, and there's some arguments that this may not be the best approach for that anyway. But yeah, if you're not worried about tracking rapid changes in parameters, then it probably makes more sense to just do this on occasion to get the parameters.
Well, let me pick up on that. You just talking about the parameters and saturation and so forth, but in general, saturation would not be reflected in constant parameters. You have some nonlinear function that you have to parameterize.
That's right.
And you can't run that through a DQ transformation and so on and so on. So,
yeah, so saturation is not something that I really want to tout this as being this approach as being a good solution for it. So we're looking at a few things right now. One thing we're looking at is doing offline characterization of saturation effects, and then incorporating those in the model, but then also including sort of a linear term, an inductance term, which we do adjust in real time. So that's one approach. Another approach is to come up with a full nonlinear parameterized model and then determine all the parameters of that model. But then that becomes challenging in various ways. What's the best model that really captures saturation with as few parameters that you need to determine, right? So that all falls into future work. But yeah, things like resistances, things like degradation effects, temperature effects, this approach should work pretty well.
kind of on the same note, presumably your current hexagon is thermal, is temperature dependent, and therefore time dependent.
So depends on how you're defining your current limit, right? Now, if you're saying it's the machine, then you're right. It's a thermal problem. You need to take into account thermal dynamics to come up with the best approach. And this leads into something that goes way beyond what I'm talking about here, which is, so you have in a car, your GPS system, the car knows where it's going somehow. Your GPS system predicts what the profile is going to be, and then it does a thermal analysis on that, and then optimizes what the best, way to use what are the best ways of using the system. So I'm digressing a lot here. If you look at the inverter current limit, then that's in some sense thermal related, but usually there's circuitry, shutdown circuitry, right? That says, okay, I can only run at this current and no further. And that's not temperature related, that's a hard limit. So it depends on how you're thinking about these things.
I have a question.
Yeah.
Is there an intuitive way to understand feature identification matrix? Like, what is it telling us, like inside the band? So it's looking at how sensitive your output is to changes in parameters, is effectively all it is. And of course, the thing about it is your output depends on your input, right? And so you have to come up with the input that maximizes that sensitivity. So simple example, let's look at a parallel RC circuit, right? So if you apply a DC voltage to that, you can figure out what the resistance is. You have no idea what the capacitance is, right? But if you apply an AC signal, that gives you more excitation,
And that gives you the information to independently determine both resistance and capacitance. And so the input determines the sensitivity. So what's the best input to get all these different parameters? Make sense?
What did the Navy have to say? Is this the next fighter jet?
This is this is basic research, either 6.1 or 6.2, as O&R likes to say. I think they want it to be 6.2. The Navy is developing the all-electric ship, right? That's a big activity. And in terms of the academic research, a lot of that is towards coming up with techniques to model and control sort of a shipboard power system. And so we actually have a new project starting up right now where we're going to collaborate with Florida State University and their CAPS system because they do a lot of shipboard power modeling. But a shipboard power system is an overactuated system. You have multiple generators, multiple energy sources, and so it's possible to apply these techniques to something beyond just like an inverter or a single energy storage system. And so that's kind of the next stage of what we're going to do. And then there's some other uses of parameters. I got into power, but we can also use these for condition monitoring, monitor state of health of a plant as well. And so these are other techniques that we're going to be looking at in that context.
The primary source is still nuclear, though?
No, it's fuel related. This isn't submarine work. It's all, so the motivation behind the all-electric ship, right, is historically, right, ships carry around a lot of energy. Some of it was to actually propel the ship. Some of it was in missiles. But it was all sort of very, allocated for very specific uses. The idea behind the all-electric ship is you have one energy source, which is fuel. You generate electricity, and then you use that for everything, for propulsions, for weapons, right? So they're doing rail guns and lasers and all these kinds of things. But that allows them to make their mission profiles much more flexible, right? That's the goal. Yeah?
How come flywheel? You mentioned flywheels kind of at the start, but this is sort of dropped off.
Yeah.
Why?
Why did I? Well, some of the research here, like some of the earlier research, was actually done as part of a DOE center that we were a part of. And that was focused more on things like buses and whatnot, which flywheels are potentially an option there. When I was a grad student, there was a startup company called Rosen Motors, and their goal was to make a hybrid electric vehicle that had a micro turbine and a flywheel. And in the past, some of the big three automakers have also investigated flywheels. But right now, with the exception of some kind of very specific applications like, racing automobiles, no one's looking at that seriously. The Navy does look at flywheels, particularly for things like their electromagnetic aircraft launch systems. We have done some work where we've included flywheels in some of these analyses. We've done some experiments with our flywheel. It's a lot harder to work with the flywheel. So if we can show the basic ideas with the battery and ultracap system, we tend to do that. And the flywheel is basically another motor generator problem. So it's similar to what I just shown. Okay, thanks.